Today we will start discussion on Boolean algebra. So, last day we have discussed that the design of digital circuits, and just to design the digital circuits, what are the basic needs that we have discussed in the introductory class. So, if we recapitulate quickly the summary of the last day's lecture, that we found that three things, that logic circuits, truth table or Boolean expressions, that any one of these things is necessary. Now, last day we have seen some Boolean expressions, that means given a digital design to be built up, first we have identified as some of the expressions, or the if the truth tables, we have seen that how the truth table can be built up from the Boolean expressions, and again from the Boolean expression the logic circuits can also be built up. Now, from logic circuit, if the logic circuit is given, from there the Boolean expression can also be evaluated. Similarly, if the logic circuit is given, the truth table can be constructed. If the truth table is given, then the logic circuit can be designed from the truth table. So, today we will see that how this Boolean expression can be built up, or what do we mean. Actually, these expressions are based on the Boolean algebra. So, first today we will see that what do we mean by this Boolean algebra, how it is the basic building block of the digital circuit design. So, from this diagram, that we will be starting our discussion on the Boolean algebra. First we see that what do we mean by this algebra. So, Boolean algebra can be defined with a set of elements, a set of operators and a number of postulates. So, these are the three basic ingredients of the algebra. Now, what are the elements? A set of elements is any collection of objects having a common property. This is a definition of set. Say S is a set, and these are some A, B, C, D, these are some variables. Later we will see what type of variables these are, and these now A, B, C, D we are calling these are the elements. So, A belongs to S, and C E is not belonging to S, because E is not as the in the set S. So, these are my A, B, C, D are my elements. A set of operators. Now, a binary operator defined on a set S of elements is a rule that assigns each pair of elements from S to a unique element from S. So, that means A, B are the two elements in the set S. So, if we take A and B, we take an operator star. So, A star B, if we compute, we are getting a element C, which is again an element in S. So, then this star is defined an operator on S. Now, a set of such operators defined on S, that we are taking as the set of operators, and third is the number of postulates. So, postulates are used to deduce the rules. Often we call that these are the nothing but axioms. So, there are some theorems and properties. Now, the basic, when we define, mainly we are define a algebra. So, when we are defining mathematical systems, we need these three things, and in between within these three, the postulates are the main one, that is the rules defined on the set. Now, what are these rules or these postulates? First thing is the closure. So, this we can tell this is a property. So, a set is closed with respect to an operator A, B belongs to S, C also belongs to S, such that A plus B equal to C. That means, we are taking three elements from S or A, B, C, and one operator star, or here one operator plus say. So, A plus B, the result A plus B is giving is the C, which is again one element in S. Then we are telling that this is a closure property. The set of, we take an example, the set of natural numbers is not closed with respect to a binary operations minus. See, if I take the operation or the operator as minus, then say binary minus, then 4, 6 are the two elements, say A equal to 4 and B equal to 6. Then 4 minus 6 is minus 2, but minus 2 is not an element in n, the natural numbers. So, the natural number n with respect to the binary operation minus is not closed. So, closure property does not hold if we take the operator as the binary minus. If we take the operator binary plus, then see we take this see, we are taking a operator we are taking a binary operator plus positive. See, then next rule is the associative law. Then we take one operator star on S, and it will be called associative if that A star B star C, that means the operator is operated first on the two elements A and B, and then again the operator is operated on the result of A and B, and C is called associative if it holds, if it is equal to the A star B star C, means the the left hand side, the operator is first operated on A and B. Then the result we get, that will be treated as one operator, and C, the another element of S is the another operand, and then the operator is again treated on this. The result we get, if it is equal to, that if the operator operates on the B and C first, and then the operator is again operated on the other element A, and the result of B star C, if these two results are equal, then we are calling that this rule is associative. Now, another rule is commutative. Again we are taking the same operator star and the same set S, that means the star operator on S is commutative if the S star B equal to B star A for all A B belongs to S. Now, one concept of identity element. What this is identity element? Again we are taking that same operator star on S. Now, if there exists an element E such that E star A equal to A star A, that means the operator is taking two operands, the E first and then the one element A, and A first and then the same element E, and the results are same equal to same for every M belongs to S. That means, M is again the result is again one element in the same set S. Then we are calling that with respect to the operator star, E is the identity element of the set S. Now, if we take one simple example, say our plus addition operator. So, with respect to addition operator on set of integers, so say A is one integer, then A plus 0, we know that it will be 0 plus A, and this is nothing but A, and A belongs to that set of integers. Say this set is denoted by I, capital I. So, A belongs to I. Then this 0 is the additive identity of the set of integers I. Now, similar to that identity element, when another concept is there, it is called the inverse element. Again, for every element A belongs to S, if there exists a B, another element belongs to S such that A star B equal to E, means if the operator star, say this is a multiplication, then if it operates on two operand A and B, and this gives a the identity element. Just now we have defined the identity element, it give the result is the identity element, then that any one of these element is the inverse of the other element. Another rule is that distributive law. So, for the distributive law, we take the two operators together, say star as well as dot on S. Now, if the A star B dot C equal to A star B dot A star C for all A B C belongs to S, then we call this is the distributive law holds with respect to the two operators star and dot on the set S. Now, see here the rule is we take two operators star and dot, and we take three elements on the set S. Now, say three elements are A B C, we take two elements B C, that is operated by the operator dot. Now, the result is operated by the another operator star, and the operand is the third operand, means the third element. The result we get, if that is equal to A star B dot A star C, what does it mean? That means that see the last operator star, that is treated in this way, that as if A operates or star operates on A and B, star operates on A and C, and then the two results are being operated by the operator dot. Then if these two results are same, then we are calling these are the distributive law. Now, if So, if we take the two operators plus and dot on the set S, then we can summarize that with respect to our identity elements, that if the binary operator is plus, that means it defines addition, then the additive identity is 0, and if we take dot as the operator which defines the multiplication, then the multiplicative identity is 1. Now, if we take one element A on S, then the inverse of A is 1 by A, and if the operator is dot, then A dot 1 by A equal to 1, because as already I mentioned that multiplicative identity is 1, then we can define that 1 by A as the inverse of A, which defines the division actually. So, if we now concentrate on the Boolean algebra, so far we have defined that the general algebra, and if we consider the Boolean algebra, we can define like that. First, the George Boole introduced this new algebra called the Boolean algebra in 1854. Now, the ordinary algebra deals with the real numbers, means the set is a infinite set, consists of a infinite number of elements. Now, here in Boolean algebra, it deals with a set of two elements, that is 0 and 1. The operators are two operators plus and dot, and rules are same as and or not. Already we have introduced that the logical and or and the not. So, how we have defined that our initial algebra, that it is a set of elements, a set of operators, a number of postulates. Now, here the set of elements is only a set of 2, 0 and 1. Set of operators, two operators we are taking plus and dot, a number of postulates, and these are the postulates we discussed that are same. Now, we remember that and or not, again if we take now from the concept of the Boolean algebra, see these are A, B are the elements. Now, the operator say A dot B, this is similar to the our AND gate. That means, this is the truth table of AND gate. Now, if we take A plus B, that plus is the operator and again the two elements are A B, then it is similar, the input output relationship, this is similar to that of OR gate. And another we are taking that if we take only one element A and the complement of A, then this is the nothing but the similar to NOT gate. So, just now we have defined the algebra, the set of, if the set of elements A B are the element, two elements, the set of operators that are plus and dot, and the rules just now we have discussed, and we just form this A dot B, A plus B and negation A or the complement of A, then we are getting actually the AND gate, OR gate and NOT gate. So, I remember that this A and this complement we can define like that. So, this is, if this is A, then actually this is the A complement, or we write negation A like that. Sometimes we write here. Now, we see the AND gate, unknown OR gate. So, again these are same of another input B, and this is my OR gate. So, mainly these three things we will be discussing. Now, we see how the rules are applicable. So, just now we have discussed the rules as the properties or the postulates we have mentioned, that first one is the closure. So, if we take the plus and dot as the operators, then closure is very obvious. See that here the two elements are only 0 and 1. So, 0 plus 0, it is defined as 0, 0 plus 1, it is 1, 1 plus 0, it is as 1. Similarly, 1 dot 1, if we take the now the operator as dot, 1 dot 1 is 1, 1 dot 0 is 0, and 0 dot 1 is 0. Now, see the results are also either 0 or 1. So, this is the closure property is it holds. Now, here the identity is 0 for plus and the identity is 1 for dot. Now, the commutative law holds. This is very obvious. From that, if we take 0 plus 1 is equal to 1 plus 0, and this is 1. Similarly, if we take dot, then 0 dot 1 equal to 1 dot 0 equal to 0. So, commutative law holds. Distributive laws hold. We will be seeing this property later. Now, the inverse exists. See that if we take again the operator plus and the element is 0, then 0 plus complement of 0 means 1. So, 0 plus 1 is 1, and similarly 1 plus complement of 1 is 0. Here see, if we take the 0 and dot as the operator and 0 as the element, then 0 dot complement means 1, complement of 0 means 1. So, this is equal to 0. Similarly, 1 dot complement of 1 is equal to 0. So, we see that here actually the inverse exists. Now, for the distributive law, see distributive law to be hold. See, for distributive law we take three elements. Say the three elements are A, B and C, okay, and the two operators are plus and dot. Now, say I am taking A, B, C, B plus C say A dot B plus C. I am doing A dot B, A dot C and A dot B plus A dot C. Now, see, we take that all the values of A, B, C, then B plus C is 0 plus 0, 0, then 0 dot 0 equal to 0. Here it is A dot B, this is also 0, A dot C is also 0, then this is 0 plus 0, 0. Now, if we do 0, 0, 1, similarly, so this is 0 plus 1, 1, A dot B plus C, this is 0, this is 0, this is 0, so this is again 0. Similarly, if we just complete this full table, then this is 1 plus 0, 1, again the same thing, then 0, this is 0, this is 0, 0, 1, 1. Now, B plus C equal to again 1, but A dot B plus C is again 0, this is 0, this is 0, this is 0. Now, 1, 0, 0. Again B plus C is 0, A dot B plus C equal to 0, A dot B, A dot C, then this is 0. Now, we do 1, 0, 1. So, B plus C is 1. Now, A dot B plus C, this becomes 1. Now, A dot B 1 dot 0 means this is 0, but A dot C is 1. So, this becomes 0 plus 1, 1. So, 1, 1, 0, again B plus C is 1, A dot B plus C is 1, A dot B is 1, A dot C is 0, this is 1. Last term is 1, 1, 1. So, this is again B plus C 1, A dot B plus C 1, then A dot B is 1, A dot C is 1, 1 plus 1 is 1. Now, see that if we do the comparison, then this A dot B plus C, see these values that are, there are 5 zeros, 3 ones. Similarly, from here we will be seeing 5 zeros and 3 ones. That means, my A dot B plus C equal to A dot B plus A dot C. So, the distributive law holds. And see here this plus and dot operator that we have defined from the algebraic point of view, this is similar to our OR and the AND operator. So, the last day what we discussed that some Boolean expression. So, now we can tell this A dot B plus C or A dot B plus A dot C, these are again the two Boolean expressions. And it has today what we have seen, actually these expressions are evaluated from the Boolean algebraic concept, that where that A, B, C, these values are can take only the 0, 1 values. That means, these A, B, C, these are belongs to S, where this A, C, S belongs to actually 0 or 1, the two values is equal to either 0 or 1. Now, we see that how these Boolean expressions can be developed from these algebraic concepts. First, we tell that one very important principle, that is the duality principle. The duality principle states that every algebraic expression is deducible if the operators and the identity elements are interchanged. So, here that operators are again that plus and dot. So, if we take see a plus 0, this is equal to a, because 0 is the identity element, additive identity. Now, if we replace the plus by dot and 0 by 1, we will be getting the same thing. Duality principles states that. So, see from the first expression, a plus 0 equal to a, plus is replaced by dot, 0 is replaced by 1. So, a dot 1 equal to a. Similarly, the second expression, a plus complement of a equal to 1. So, plus is again replaced by dot, negation a dot negation a equal to 0. So, 1 is inverted, a plus b equal to b plus a. So, similarly, a dot b equal to b dot a. Now, a dot b plus c equal to a dot b plus a dot c. So, if we now replace, so this first dot is replaced by plus and the second operator, this plus is replaced by dot. So, the left hand side of the expression becomes a plus b dot c and the right hand side of the expression becomes a plus b dot a plus c. So, this is the mainly the duality principle. If we consider only the postulates, basic postulates of the Boolean algebra, then it shows this type of property. Now, one very important law, we call that De Morgan's law, that we are telling. Now, there are two laws which allow us to convert between forms of logic equation and also to convert between types of get used. See, just now what we have seen, that here that actually the plus is replaced by dot. So, what we can tell that if we see that plus is nothing but our OR operator. So, this our plus is OR operator and dot is AND operator. So, these two operations I can simply tell that these are 2 input AND gate and 2 input, this is 2 input OR gate and this is a 2 input AND gate, and this 0 and 1, see there first is convert between forms of logic equation and also to convert between types of get used. That means, the plus is replaced by dot means nothing but the conversion of between two types of get and OR. So, what we can tell? That plus is the AND OR operator and dot is the AND operator. Now, we see the laws. The first one, that when n variables are ANDed and then inverted, result will be 0 when all n variables are 1. If n variables are inverted, the result or the output will be 0 only when all n variables are 1. What does it mean? See, I am taking, if I write the expression, I am taking n variables a, b, c up to n. These are n such variables. Now, first they are when n variables ended. So, they are ended. So, this dot means these are AND operation is being done. Now, the whole thing is inverted, that means the complement of the result is taken. Now, the result will be that if the every variable, each of 8 variable are inverted and then it is odd, that means a bar, it is inverted means a bar plus b bar plus c bar plus n bar, and then it is taking odd, then this is same. Now, if we take the thing, say what it is written, that a, then b, it is ANDed, c up to say n such variables, and then the whole thing is inverted. Then the result will be, it is told that result will be if each of the variable is inverted, that means say a bar dot b bar dot c bar, then it is dot n bar, and all the dots will be replaced by plus. So, these will be replaced by. So, now if we draw, say this is nothing but a dot, means what we call that a dot b is nothing but a 2 input AND gate. This is a 2 input AND gate a b, and this plus means that a plus b, this is a 2 input OR gate, this is a 2 input OR gate. So, now if we extend the operator for n such variables and we write this thing, then see this, the left hand side will be say I am taking a n input AND gate a, b, c dot dot up to n. So, this is a n input AND gate. Then the output is inverted. So, I put one inverter here. So, this is my the logic circuits of the Boolean expression represented by the left hand side. What will be the right hand side? Right hand side, see if I take one n input OR gate, then the input will be inverted of the variables or the elements that are used in the left hand side. So, in the left hand side the variables were a, b, c up to n, here all are converted. So, this is if so, this is my output y, this will be my output y. Now, these two are same. So, in this way we can convert the logic gates, that means that actually here how the AND gate is converted to the OR gate, that rule is mentioned by the De Morgan's first rule. Now, we see the second rule. See, when n variables are odd, totally reversing. Now, here the n variables are first odd, that means the OR operation of the n variables, and the only combination leading to a 1 occurs when all n variables are 0. So, again this is, then it is inverted. And what do we mean by this term? The only combination leading to a 1. See, if we do that, okay, first we describe that rule, that a plus b plus c plus n, if it is inverted, then it will be similar as if each variable is inverted and then it is ANDed with each other. And the rule says that n variables are odd and then inverted, and if n variables are inverted, the result is ANDed, the output will be 1 only when all n variables are 0. Okay. Later first we explain this term. See, the second rule we call that, again we are taking the n such variables and they are odd and then it is inverted. Then De Morgan's law tells that if we take each variable inverted, a bar, b bar and then up to n bar, and we take, instead of plus operator we are taking as a dot operator, then it will be the result. So, the first rule tell the reversing. Now, what will be the, if we take the logic circuits, then it will be the left hand side will be a n input OR gate, A, B and it is inverted, and say this is my y. What will be the right hand side? Right hand side will be a AND gate, again all inputs are inverted, again this will be y. So, these two are same. Now, the first one we have seen that how from AND gate the OR gate can be derived, here from the OR gate how AND gate can be derived. So, mainly that if we interchange the plus by dots and the each uncomplemented variable be complemented, or that non inverted elements are inverted, or vice versa, then it will give the same results. Now, another thing is that when the left hand side will produce a 1. See, for the second case, that it is a n input OR, and what is the 2 input OR truth table or truth logic? If it is a 2 input, we remember that A, that means A plus B, say 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. See that out of 4, that 3 cases it will be 1. That means, if any one of the input variable is 1, then the output is 1. So, if we now extend this concept, that for n input OR gate, if any one of the n variable is 1, then output will be 1. So, that means, from this A up from this A, B, C, from n, if any one is 1, anyone either A, C or A 1, then it will be a 1, and left hand side is actually the complement of the whole thing, the n input OR gate. See the results. So, it will be 0. So, that means that if any one of the n variables A, B, C up to n, or the n number of variables is 1, then the output, actually left hand side output, y equals to 0. So, when y will be 1? So, y will be 1, y equal to 1 when this A plus B plus n, this value equal to 0. When this value will be 0? When every variable of this n number of inputs equal to 0, then only, that means 0 plus 0 plus 0 plus 0, then only the output of the, see that output of the OR gate here, actually this output of the OR gate will be 0 when the each of this A, B, n will be 0, and if this value is 0, then y equal to 1. So, now if we see the results, that when n variables are ORed and then inverted, the only combination leading to a 1 occurs when all n variables are 0. So, this is the explanation of the first statement. Now, if n variables are inverted, the result ANDed, and the output will be 1 only when all n variables are 0. So, if we see now the previous one, that means see right hand side is a n input AND gate, and all the inputs are inverted variable. So, if we take the just like the AND gate, two input AND gate, what is the logic? So, this is A, B, Z, and the truth table of this is 0 0 0 0 1 0 1 0 0 and 1 1 1. So, this is the truth table. Now, what was our right hand side of the second rule? This is A complement dot B complement dot C complement up to n complement. Now, when it will be 1? Because we have already seen that our left hand side becomes 1. So, when it will be 1, only from the two input AND gate we are seeing, this is the only situation that when the output becomes 1. What is the situation? That when all the input variables are 1. So, if this is a n input AND gate, this is a n input AND gate, then all the inputs should be 1, and what are the inputs? A bar, B bar, n bar. So, that means all of these inputs should be 1. Now, if this becomes 1, that means my A bar should be 1, B bar should be 1, similarly my n bar should be 1, and what does it implies? This implies my A equal to 0, B equal to 0, and similarly my n equal to 0. That means, all the variables, when all the variables are 0, then only it generates a 1 output, and this is the only situation of the second rule, De Morgan's rule, that when 1 output will be generated. That means, when all the input variables it is not inverted or that non-complemented or uncomplemented variables are zeros. So, if we see here, every variable of this n number of input equal to 0, what we have achieved from the left hand side also, and only this time that that output becomes 1. And similarly, if we see our the first rule, that when n variables are ANDed and then it is inverted, and it is ANDed first, then it is inverted, and it will be same as that of OR, n input OR of the inverted variables. In this case, the case is reversed, means the result will be 0 only when that every variable or each variable of these n numbers will be 1, because only that is the situation of the AND gate. When all the inputs are 1, the output will be 1, and then it is the complement. So, it will be this becomes 0. So, this becomes 0, and when it is a is 1, that means all the variables are 1, means the each individual term will be 0, and then 0 plus 0 plus 0. This is the only cases of only one case of the n input OR gate when it generates a 0 output. So, this explains that when the output of the left hand side will be 0 when all the variables will be 1. Similarly, for the right hand side also the output will be 0 when all the variables n variables will be 1. So, today we finish these lectures here, but we see some of the quiz questions for the last class also. See that for lecture 5 and 6 together we are giving some of the quiz questions. So, the first question is the two inputs A and B are inverted and applied to a NOR gate. Construct the truth table. Second question is an input A is inverted and applied to an AND gate. The other input is B. The output of the AND gate is applied to an OR gate. A is the second input to the OR gate. Draw the logic circuit and the truth table. Question 2 is from the lecture 5. Draw the logic circuit for the Boolean expression z equal to A dot B bar, means B complement, plus A bar dot B plus A plus B bar dot A. This can be anyone, we can follow any one of the lecture 5 and 6 we can follow. In the lecture 5 I have given the Boolean expression and the truth table, and the lecture 6 we have discussed from the Boolean algebraic point of view. So, any one of the concept we can apply to solve the question 3. So, these are the 3 quiz questions. So, we end the lecture here. Today we will continue the discussion on Boolean algebra, but before that first we see the answers of the last 2 lectures quiz, the lecture 5 and 6 quiz. So, the first question